So good evening to all. So this will be a demo session as Ivan has already given a hands-on session of lead-driven cavity and 2D channel flow. So in today's session, we'll see the meshing in 3D pipe using block mesh, then the setting of the test case, and we'll see the post-processing. So as in the previous session, Ivan and Professor Hari has already explained how to change the test case and how to modify the block mesh. So I will directly come to the explanation of block mesh. So in today's session, we'll cover these three portions. So as this is a 3D pipe, so in 3D pipe, we'll divide this block into these many vertices. So in the block mesh, as previously explained, we have to first define the vertices. So in the pipe, there will be a inlet section and outlet section. So for both the sections, you have to define the vertices in this fashion, so that you will able to properly uh, grade or discretize this block in a particular manner. So in today's case, we are defining the radius of the pipe as 0.01 and A being a origin of this cylinder. So this is the inlet section and this is the outlet section. Now after defining this inlet and outlet section, that means the vertices, uh, and also I have given the naming what is this 0 and 1 vertices. After this, we have to define the number of blocks. So as previously explained, the number of blocking will be defined in as per the right hand rule. So here a right hand rule or anti-clockwise direction. So suppose I have to define this first block, so it will be in the manner of 0, 1, 2, 3. So likewise, we have defined here 5 blocks. So after defining these 5 blocks, we have also given the grading of 10, 10, and 200. So this will be the X grading, Y grading, and 200 will be the grading in the Z direction, as this is a 3D block. And everywhere I have kept the uniform grading. That means in X, Y, and Z, everywhere it is a uniform grading. So after defining these vertices and block, the block will look something like this. So these are the 4 outer block, and this pink one is the inner block. Now we have to, as this is a 3D pipe case, so we have to define the arc also. So defining arc means to these outer edges, means that means this 9, 10, 10, 14, 14, 13, and 13, 9. So for these 4 outer edges, we have to define the points. So based on that, it will define the curve. This edge, we will define the arc. So this 1, 2, 2, 6, 6, 5, and 5, 1 is the edges at the inlet section, and this later 4 will be the edges at the outlet section. Define the point. So based on that, it will create an arc around those edges. So you can see after defining these edges, this kind of mesh will get able to get. Based on this, I can show you also how these files are. So as I have explained, that first we have to define the vertices. So these are the vertices at the inlet section, and these are the vertices at the outlet section. But then coming towards the block, so these are the blocks which we have defined here. So we have divided the whole pipe into 5 blocks. Now, after defining the blocks, here we are defining the arc, so that it will properly take this circular portion. And after defining all these blocks, edges, and vertices, we'll define the boundaries. So based on the vertices, we'll define which one will be the inlet, which one will be the outlet, and which one will be the wall. So let me show you from the PPT. So this patch will become inlet. The patch opposite to it will become outlet, and this surrounding wall, that means this 9, 10, and 2, 1, this will become the wall. So like that, 4 walls are there, and I'm defining these 4 walls under this patch name called wall. for generating the mesh, again, same block mesh command you have to run. So once meshing will be created, we can check the mesh in the para view. After loading this mesh file, you can see we are getting a cylindrical domain or a pipe, and this is the mesh. So this is my Z direction, and this face on the XY plane. And you can see the patches we have defined here: inlet, outlet, and wall.
Oh, one question. So in the block mesh dict file, we are specifying the each and every point there, right? So
Yes,
those things are has to be manually entered, calculated, and entered.
yes,
How,
yes,
how
yes,
does it?
yes. Those things you have to be
All
manually enter. So let me show you. So suppose for this calculation, we have to first define the radius.
okay.
So based on this radius, you have to do these calculations so that you will get this 0, 1, all these points.
One second. Just I'm just trying to understand this
Okay, okay,
manually.
fine.
So you are saying like whether this can't be given as a assigned as a variable and then entered. I mean, like using the dollar sign,
Yeah, that is
or
also possible. You can give it as a variable also.
okay, okay, okay. So here at every point this angle remains the same, right? So and
Yes,
then
yes.
okay, okay,
As this is a circular geometry, so that's why the angle remains same.
okay, okay, okay.
Okay.
What is capital A here?
So capital A is the width of this inner square. So that you have to fix by your own. Okay.
Okay, fine. Thank you.
The mesh has got block mesh has run successfully, but if I have to open the mesh manually from ParaView, how do we open it?
So in ParaView, okay. So in ParaView, you can use this paraform command.
Okay.
Is it working for you or?
No, in the left hand side you have built-in and then your mesh model is available. The mesh model is not visible for me. I'm using different things.
Correct.
So just
So
what?
yeah, let me show you again. So your paraform will be open. You have to click here, apply,
Okay.
and you will get your geometry and mesh. And you can check using this surface with edges. You can check your mesh also. Are you able to check the mesh?
Yes, it's coming. Yeah, visible.
Okay, fine.
Okay.
Okay. So we'll move forward with the boundary condition. So after developing the mesh, so these are the patch which we have already defined in the block mesh file. So these things I'm skipping for now. So because this Ivan has already covered that zero means in zero folder will define the boundary condition. Constant means all transport property will define. And this is sorry, uh, this is my mistake. So in the system folder we'll define the discretization scheme, solvers, and control dict. So this I am skipping for. So inside the zero folder, so there will be two files, U and P. So in U file, you have to define the inlet velocity at the inlet, outlet I'm keeping as zero gradient, and wall will be no slip. And P is the pressure. So if you are defining some fixed value at the inlet, you have to give zero gradient at the inlet for pressure condition, and outlet will be zero pressure. And similar to that, zero wall, zero slip condition, that means zero velocity you are defining here, fixed value zero. So similar to that, for pressure, you have to define zero gradient water condition at the wall for pressure. Now coming to the constant folder, there transfer properties will be there. So for this case, I'm defining the kinematic viscosity as 0.0001, and based on velocity and kinematic viscosity, the Reynolds number is coming around 200. So that I will show here also. So inside 0 folder, these two files are there. Yeah. So in U, the inlet condition is fixed value, and I'm defining velocity in the Z direction because my geometry is along the Z direction, as you can see. So this is my XY plane. So on XY plane, this circular cross section is there, and the geometry is along the Z direction. That's why I'm defining the velocity in the Z direction. That is 1. Similar to that, outlet will be 0 gradient and wall will be no slip boundary condition. And based on that, pressure boundary condition will be defined. That is inlet 0 gradient, outlet 0 pressure, and wall 0 gradient. Also, we'll see the transport properties. Yeah. So in transport properties, we are defining the kinematic viscosity as 0.001. And this transport model is nothing but we are simply defining whether our fluid is Newtonian or non-Newtonian. So for this case, I am defining the fluid to be Newtonian. Now coming to system. This file was previously explained by Ivan. That what are the functionality of FE scheme, FE solution. But once again, we will cover it. So in FE scheme, we'll define all discretization schemes. For DDT is nothing but the temporal term. Gradient scheme will be the pressure gradient term. Divergence will be convective term, and Laplacian will be diffusive term. So this Gauss linear is nothing but we are discretizing the equation for that particular term using center difference approach. Now coming to FE solution. So these are the metric solver we are defining for U and P. Now coming to the control dict. So here we will define which solver we are using. So currently we are using ICO form, start time, end time, and what will be the delta t. Delta t means the step size with which the simulation will proceed. Now after setting all these things, we'll go to terminal and we'll simply type ICO form and we'll start the run. So as this is a 3D geometry, so simply typing ICO form will take time to run. So for that, I have already run the cases and I have the results, so that I can show. So this is the pipe case, flow through pipe. So this is the pressure which is showing how the pressure will vary from inlet to outlet. So as you can see, at the inlet there is a high pressure and towards the outlet there is a low pressure. So the flow will be from high pressure to low pressure. And to check the velocity, you can simply select velocity. So as you can see on the wall, it is showing 0 value because we have given the 0 wall boundary condition at the wall. So for checking the internal flow or how the internal velocity is there, so you have to select this slice option is there. So select the slice option. It will ask in which direction we have to slice your geometry. So we'll select X because we have to see inside of the channel. So it has sliced the whole channel into 2D plane. Now we'll be able to see how the velocity is inside the flow domain. So as you can see, this is for the time step of 0.005. As we'll move forward, the velocity will keep on developing. So as you can see, we have given a constant velocity at the inlet. So for the time step of 0.005, it is almost a constant velocity at the internal of the pipe also. But as the time proceeds, it will slowly get developed. And you can check this velocity profile using this plot over line, which Ivan has explained previously. So we'll select this. So we'll plot at some middle section of this pipe. And when you press apply, from here you can untick pressure. And this is how your velocity profile you will get. So at the initial time step, the velocity profile is something like this, more of a uniform kind of thing. And as the time proceeds, it will slowly get developed. So this I can show you using some animation also. So this is how the velocity profile is getting developed over the period of time. And we are getting a smooth parabolic velocity profile once the solution gets converged.
Sir, is it possible to make the flow fully developed at the inlet from the start of the flow? I mean, to ensure the fully developed condition at the inlet.
Yeah, that also you can ensure by giving some equation at the inlet boundary condition.
Using UDF, like UDF, right?
Yes, yes, correct.
Okay.
Okay, so you can save this data also so that you can plot this data for, or you can compare with some other data set using spreadsheet view. So from here you can save this data for this line, and this is how you will get this plot. So this I've saved the data for different time steps. So you can see I've saved the data for 8 different time steps, and this is how the velocity profile will get developed over the period of time.
Can you repeat how you brought that data?
Yeah, okay,
That,
okay, fine. So from plotting you want to see, or
plotting I am aware of that plot from you selected
okay,
plot
okay, I
from
will show
line,
you.
right?
Fine.
Yeah.
So till slice it is clear, right?
Yeah, yeah.
Okay. So for plotting, see here one option is there called plot over line.
Okay.
Okay, select this plot over line. Some random line will come. Okay.
Okay.
So as this is our y-axis, this width of the pipe is along the y-axis. So here some axes are given, x, y, and z on the left hand side. Okay.
Okay.
So select y and click here apply. So you will get here P and U.
Okay.
Okay. So scroll down in the left hand side, untick P. So you will get velocity profile. Okay.
Okay.
Now to save this data, simply go here. Some split window option is coming.
Okay.
Okay. Click over here. Then there will be many options are given here. So
Okay.
further
Okay.
scroll down and see the last option is spreadsheet view.
Okay. Okay.
Okay. Click over spreadsheet view. It will give you the data over that line.
Okay.
Okay. Now to save it, see the last option is export spreadsheet.
Okay.
Okay. If you click over here, it will ask you to save this data in
Okay.
.csv format. CSV format is nothing but it is similar to Excel format.
Yeah.
Okay. If you press OK, it will save this whole data.
Okay. Okay. Fine.
Okay. So you can check it from here also. This file we have saved just now.
Okay. Okay. Thank you.
Okay. Yeah. So this is how you can save the data. Then again for checking the streamlines or glyph or the velocity vector on the same slice, you can select this glyph, change the scale array. Yeah. Now, as these vectors are very big, so you can scale it down using this scale factor. This is how the velocity vectors are coming inside the flow domain. So you can see near to the wall, the velocity vectors, the value of velocity vector is very small because of no slip condition. As you will move toward the center of the domain, the velocity will increase, and that's why the length of the vector are large. Now, if you want to plot the streamlines also, so this stream tracer option is there. You select the stream tracer option. So this line will tell you that the stream tracer you want all over this whole domain, or you can change it to instead of line. You can, so this is like a seeding portion. Instead of line, you can take a point cloud also for changing the type of not type but the streamlines how you want, and you can change the seed number of points also, so that it will increase the streamlines. So if you further increase this number of points, you will clearly get the streamlines all over this domain. So as this is a straight type, so you will get a straight streamline all over this domain, and no, you will not see any further changes in the streamlines. So this is how you will get a fully developed velocity profile in a 3D pipe. So any question is there, you can ask.
Sir, is it possible to plot the velocity magnitude at different time step in a same plot using the same set of paraview?
Yes. You can do it. So that's what I was showing. See, suppose on the line you are asking, right?
The line at different time steps.
Okay. So suppose I'm plotting over this line. So you can change the time step from here also. See, currently I'm at the initial time step of 0.005. As you keep on increasing the time step, the plot will also change.
Yeah, but we accumulate it on a same plot. I mean, same graph.
Oh, same graph you are saying?
Yeah,
No,
not with the manually doing it, but can we do it in the same interface?
Same interface? I don't think so. For that, you have to save the data at each time step, and then you have to plot
and
it.
Then later post process it, right?
Correct. Yes.
Yeah. Okay. Fine.
The way I've showed it here, like this, you want it, right?
Yes. Got it.
Yes. So you have to save the data at each time step, and then later you have to do the post processing for plotting.
So I have a question, like how we can calculate the drag value, or if any other variable is available in the zero folder, just like U and P.
Okay.
For some cases, we have to calculate the theta value, tau value, stress values, and
Correct.
can we see that values directly in the para view, or we have to calculate by other way?
No, you have to calculate. Means drag value you can take it, but for that you will require the drag coefficient, right?
Okay.
So drag coefficient, there are many utilities given in the open form.
Okay.
So using that, you can calculate the drag also. So if you search it in Google, drag coefficient, you will get a function. That function you have to keep it in control date for calculation of the drag value.
Okay. Or
like
there's
that you
a
can
kind
get,
of provision like calculator, like just like I'm seeing this calculator here. Can we put a formula in some form?
yes, yes, like that also you can do it. So one calculator is there, this option you are saying, right?
Yes.
So using that, suppose using P or U is
Okay.
some other variable you want to calculate, you can calculate like
Like
wall
just
shear
like
stress you can get.
velocity, I mean, want to
Yes.
calculate by this way.
So wall shear stress you can get it.
Okay.
So for wall shear stress, let me show you in ParaView itself you can get it. So go to filters. So here gradient option is given, right? So click on this gradient option. So you can here itself calculate the gradient of here, velocity. So here you have to select the velocity. So here you can compute the gradient. Even vorticity also you can calculate here itself.
Mhm.
And once you press apply,
Okay.
so in this drag menu, you can get the gradient and vorticity also.
Oh, nice. Okay.
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 But if you want to lift and drag both, that you have to get it using some other utility.
Okay. 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 Thank you,
Okay.
sir.
I'm a bit of trying to understand how you mesh this profile
Okay.
mathematically. I didn't understand that part clearly. Is there any proper tutorial there?
Means what you have not understood.
I'm not understand how you gone about this. Like
Okay. So see, we have for getting this circular profile, we have defined
yes,
a square inside this, right?
okay,
Okay. So square, if I'll from center, if we'll take this
radius. You take the radius.
radius, so it will be at an angle of 45 degree, right?
Okay,
So to get this point, this will be y and this will be x. If you resolve that radius in based on 45 degree,
yes, okay,
okay, so it will be r for r cos 45 and r sin 45.
okay,
Okay, so like that you will get
okay,
this 0.1.
okay,
Okay, so based on that, if you want to get 0.2, so it will be on the negative x-axis, right?
okay, okay, okay,
Negative x and positive y.
okay.
So like that, it
That
will
is
be
true.
minus
That
r
is true.
cos 45 and r sin 45.
Okay, okay.
One small doubt here. So you said the capital A is the length of the side of the square.
Yeah, this is small square.
Okay. Capital A belongs to the length of the small side of the small square.
Yes.
Then what is the length of the bigger square side?
So bigger square I was only explaining. So that will you have to calculate based on this radius.
Capital A we have to calculate.
Yeah, A you can assume something.
No, no. I mean like that small A is the center, right? Center of the pipe.
Small a is the center of this pipe or channel.
Yeah. Channel, and then we are just defining only the small square inside the pipe, not the bigger square.
No, bigger square also. See, this 0.037 and 4 is for the smaller square, and 0.1, 2, 6 and 5 is for the bigger square.
Can you differentiate what is
Okay.
capital A and what is small a? I'm not getting it. Sorry.
Okay, in the same fashion, we need to assign a different variable for the bigger square's length, right?
So bigger square, that or only I was explaining. So bigger square you can define using this radius. So it is a square. So the diagonal angle from this horizontal will be 45 degrees, right?
Yeah.
So how you will get x and y using this radius? So it will be r cos 45 and r sin 45.
Okay, understood. Okay. Fine.
Got
Okay.
it? So like that you will get 0.1, 0.2, 6 and 5.
Okay.
Got it?
Okay.
Sir, what is capital A, sir? I didn't get that properly.
Oh, so capital is the length of this smaller square.
Yes, sir. Length of the smaller square. Sir, if you put a capital A that is cos 45 for 0 means you are only getting that half length, right? You are not getting the full length, right?
Sorry. It should be a by 2. Sorry.
Yeah. That is a mistake. Okay.
Yeah,
That should be
sorry
able
for
to.
that. Sorry for that.
Okay.
Now it is clear?
Yeah. Okay. Now it is clear.
Fine. Yeah, someone was asking about this second slide.
Yes. Just Then there was a visualization in ParaView for the different sections.
This one.
Yeah.
This one, right?
Okay. Yeah. Okay, fine.
Okay.
Sir, what if it is an hollow cylinder? Like,
Okay, hollow in the sense?
if there is a solid geometry inside and the flow is flowing around axially,
Okay.
Maybe we call
in
it
that case-
annular region.
like an annular region, yeah,
Annular
annular flow.
region, yes.
Yeah.
So in that case, you don't have to define this inner cylinder.
Yes,
This
we
square
don't
you are
need
able
an
to follow,
O-grid
right?
mesh, yeah.
So currently what we have done, so we have defined in blocking all 5 blocks, right?
Okay.
These 5 blocks we have defined it here, right?
Yeah.
So instead of defining all 5 blocks, we will only define these 4 blocks and will not define this inner one.
Okay.
So if you
And then
if you
we
not
make an
define
arc
this
there,
inner
right?
one, you will only get this outer thing and it will be hollow from inside.
Okay.
Okay.
Yeah. Okay, thanks.
Yeah. So here also I can show you. So these 5 blocks we have defined. So we will not define this last one. We'll only define this 4. So you can try now also. If you delete this or you can comment it, this last block, you will get a hollow in that section.
Okay. Fine. Thanks.
Yeah.
Sir, creating mesh for this internal flow, you have a reference point. Like so you try to do with a circle. You have
Yes.
a outer circle. You go with the reference points.
Yes.
What about the creating mesh for that external flow?
Okay. For the external flow, you are saying. Okay. For external flow, it will be different. So suppose flow past a cylinder you are referring, right?
Yeah, we don't have any reference point at all. That's the rule.
Okay. So for that, again, over this, you have to define a bounding box, and based on that, you have to create a mesh.
So arbitrarily, we have to create a points,
Yes.
a surface.
Yes.
Okay. So that means we have to create a control volume. So
Yes.
based on the control volume, we have to.
So for that, I think one tutorial is also there in
Okay,
the
sir.
open form tutorial.
Okay, sir.
Called as a 2D cylinder or something. Ivan,
Okay, sir.
is this right?
For OpenFOAM, there are cylinder tutorials. But they wanted something. I heard somebody saying about annular.
No, annular I have explained, but they are saying that
External
flow.
flow.
External flow.
So you want external flow over a cylinder, right?
Yes.
There are cases in which they've done external flow over cylinder. You can see in the tutorial cases as well. And there is, I think, a GitHub page also on which you can find those.
Okay, sir.
Yeah.
Okay, sir. Okay. So I'm trying to understand this one. So do you go for meshing? You go with any standard procedure, or by just random mathematical intuitions? You go with trigonometric intuitions.
No, you have to do some calculation for that.
Yeah. Okay. Okay.
It will be based on what kind of geometry you are having. Suppose pipe flow.
Okay.
So what Reynolds number you want.
Okay, for meshing, I guess. I'm
Yes.
trying to understand them. Yes. Okay. Okay, sir.
Okay. So any other questions are there or?
So this is like completely off from the topic. Suppose if we have an aircraft, since I'm an aeronautical student. So if we have an aircraft, so usually in ANSYS what we do is we create a domain and then we apply the boundary conditions, the meshing, everything is done.
Okay.
So if we design it in a separate CAD software and if with the MSH file, like for ICM, we'll have to use the MSH file. What do we have to do for the CAD files that we want to import into OpenFOAM?
So using that CAD file, you want to create a mesh, you are saying?
Yeah, in OpenFOAM and do the analysis in here in OpenFOAM only.
Okay, so if CAD file is there, there is a meshing tool available in OpenFOAM called as SnappyHex or CF Mesh is also there. Okay, so using that, you can use the STL file to create a mesh.
Nikhil.
Yeah.
See the motorbike case that you opened, you can show that to them.
Okay, fine.
That is a good example of use
Correct.
snappy hex.
Yes.
Yeah.
So you can see this tutorial, ma'am.
Okay.
So this motorbike case. So in this, they are using snappy hex mesh. If you see this snappy hex file,
Okay.
so inside this they will define the STL file.
Okay.
Yeah. So here they have used some different
File type.
not STL CAD model
Okay.
dot OBG, and instead of this you can use dot STL also.
Okay.
Okay. So it will create a bounding box and it will start meshing over it.
Okay. Sure.
Okay. So you can go through this tutorial inside this incompressible simple form.
Motorbike and system.
Motorbike, yes.
Yeah.
Okay. So this you can check.
For the 3D pipe case, can we increase the mesh in the center?
Okay.
Yes.
Can we get mesh at the
Increase finer mesh at the center.
Yes. So in the block mesh, if you'll see, so these gradings we have defined, right? X and Y. So X and Y, if you increase, let me show you also. So if I'll give 30, it will increase the meshing in the center region. So from 10, we have defined now 30. So if I'll give block mesh now, yeah. So we have created the mesh. Now we can see. So as you can see, this was the previous mesh. So now we have increased the meshing in the XY region. So after increasing the XY grading,
Can we see it from the doing slice or what?
yeah, we can see it. So this is how you will get it.
Can I use this pipe section as a vertical column also?
Yes.
Yes, no?
Yes.
I have to just change the orientation line.
Correct.
Okay, in the block mesh only. I have to just define the X, Y, and Z directions.
Yes.
Okay.
In ParaView, how to create an animation to see the flow developing actually in along the pipe section.
Okay. So once your simulation is completed,
okay,
you know how to open it in Paraform, right?
Yeah.
So after opening it in the Paraform, you will get something like this, right?
Okay.
So you have to go to this slice portion. This you are able to see slice.
Yeah.
So click over here and apply.
Okay.
So you will get a plane which will show you the internal of the pipe.
Okay.
Okay. And then instead of P, you can check U and simply change the time steps. You will able to see how the velocity is getting developed inside the pipe.
But I mean, like, what I'm trying to ask is like we plotted the graph at that time, right?
Oh, plot you want?
No, not the plot, but similar to the plot, but in the visualization, can we bring it here?
Visualization in the sense in this.
Yeah. In this contours, the shape of the plot as a contour itself.
Okay, that also you can do it.
I hope you
I
get
think
it
like an
right.
ISO surface maybe.
Yes.
Yes.
Something
Yes.
like that. Yes. So ISO surface can only be plotted using scalar quantity. Okay. So instead of scalar quantity, ISO surface, you can plot it something like this also. So using this option, you can, I will show you again. So you want to contour something like on this pipe section, right?
Yeah, yeah.
So go to slice again. So select Z so that it will going to slice this whole 2D pipe in the Z direction like this. You are able to see this section?
Yeah, yeah.
Apply. You will get a single line over this.
Okay.
Okay. Then go to filters, and one option is there called wrap by vector.
Okay.
Okay, select this and apply. You can scale it down to properly see it, and you can visualize. So you are able to see this curve. So as
Yeah,
you move
yeah.
forward,
Yeah.
the shape of this curve will also change.
Okay, 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 okay.
Okay.
Wrap by vector. Okay, okay.
Yeah. You are able to see this curve, or
Yes,
should I
yes.
change the? Yeah. Now I think it is more visible.
Yeah, yeah, yeah. Fine. Thank you.
Yeah.
What other kind of data we can calculate from here? Like just like velocity profile and the pressure profile? How
So
we
earlier
can,
I was showing the vorticity also, right?
yes.
So as this is a steady state, you will not get much in the vorticity variation, but still you can calculate it.
Or if I
Or
want
wall
the
shear stress, you
animation
can
of
get it.
this, then how I can extract this?
Oh, okay. So to see the animation, so suppose this is my channel. So go to this save animation, and you can save it either in PNG format or MP4 format also you can save.
Okay.
Okay, so you will get a video of it.
Okay. Thank you.
Sir, I have tried that annular flow block meshing,
Okay.
but when I'm trying to comment the last line and then rerun the block mesh command, it's showing a fatal error that it fails to find the neighboring faces.
Okay. Just a
Sorry.
minute.
Yeah.
So you have simply commented this one, right?
Yeah.
So not only that one, you also have to remove those edges name or edges from this boundary
That
path.
contains that file.
Correct.
Okay.
Okay. So suppose in the inlet,
Okay.
what are those edges? That also you have to comment from outlet also.
Okay. Fine. Yeah.
Okay.
Thanks.
I had another doubt.
Okay.
Suppose we have the pressure values and then we want to import it on the body, like to find out the displacement or the deformation taking place. So how do we do that? Like,
No, deformation in the sense because this is a rigid wall, so you will not get any deformation here.
okay.
Okay.
So no structural analysis can be done in the software, is it?
No, you can do it, but for those some other tutorials are there.
Okay.
Okay.
Yeah.
So for this tutorial, we have assumed the outer wall is rigid, so you will not
Okay.
get any deformation.
Okay.
Sir, will we be covering the coupled phenomena also?
Coupled in the sense?
Coupled in the sense, since the tutorial we are having only on momentum equations,
Correct.
and I usually work where I have to also solve for the case of heat transfer.
Okay.
So problem where we have both heat and velocity equations.
Okay.
Will there be any tutorial?
I exactly don't know. Ivan, can you answer this?
So what exactly is the problem?
So he want to know whether we are covering the heat transfer related tutorial also or not.
Yeah, heat transfer and multiphase will be, I think, day after tomorrow. Heat transfer, wait, I'll just check the schedule and let you know, okay?
Yeah, multiphase is there, but I'm not sure about heat transfer.
Basically, my question is problems where we have momentum equations and energy equations.
Equation.
Yeah, and both are coupled.
Okay. So for that, you can go through these tutorials. Inside this tutorial, there is heat transfer section. Okay.
Yes, sir.
So these buoyant pimple and buoyant simple form, these are kind of a coupled tutorial.
Actually, I was working on some problems, so since it's more difficult to solve, so I have reduced my problem only to momentum case. That's why
Okay.
I was.
You can go through these tutorials. So these are kind of coupled.
Okay, sir. I will try that.
Yeah.
Yeah, and Mr. Himanshu, to answer your question, we don't
Yes.
have purely for heat transfer, but it is mixed with basically we have a pressure driven case and all scheduled for this workshop. But if you want to see a proper heat transfer in which we had conjugate heat transfer, we had done that in a workshop in November. I'll share the link of that workshop in the chat so that you can refer to that as well. Okay.
Sure, sir. That will be much benefit.
Yeah.
So any other questions are there?
So when I tried running the pipe flow case, I'm getting as again solution is not converged and segmentation fault.
Which pipe case you are referring?
The 3D, I was just trying to run it, sir, but I'm getting core dump, floating point exception, something, sir.
Okay, which solver you have used?
Icoform, so that was what they had.
Icoform only, yes.
I don't know, but I'm not understanding why the current number is shooting up after a few time steps, sir.
Okay. It should not happen. Have you changed the meshing?
No, sir, I didn't change anything, sir.
Okay. Whatever the mesh is given in the test case, the same mesh you have used and it is shooting up. The current
Yeah,
number is shooting
initially,
up.
yes, sir. Yes, sir.
You can change it by reducing the delta T in the control dict file.
Reduce the delta T.
Yes.
Any number, sir, or can I just reduce it?
Currently it is point.
001, I guess.
0.001. So you can change it to point 0005 also.
0005. Okay, okay, sir. Else, how can I fix this if it repeats? Sir?
No, if it is shooting up, then you can try to reduce the delta T to stabilize your solution. Okay.
Okay. Or what else could be the possible reasons, sir, apart from this?
A reason we cannot say without seeing the error or test case what you are trying to run. Okay. So initially, if something the solution is shooting up, the first thing you should do is try to reduce delta T. If still it will shoot up, then you can change some schemes or something like that. You can change from second order to first order scheme. You can change.
Okay, sir. I'll try this.
Yeah.
Thank you, sir.
Yeah, so there's one doubt regarding setting delta T and writing the interval, right interval.
Okay.
Yeah. So your delta T, if you have a very complex case and your current number is basically very high. So in those cases, you can reduce your delta T. Now again, your delta T will purely depend on the mesh size itself. So you have a formula for that. If you can determine the smallest cell size, you can set your delta T accordingly. And so your right interval is basically the amount of iterations, after how many iterations you want it to write a file. So now in this case, if you're setting it to 0.001 and your write interval is 5, after every 5 iterations, it will basically write a file. So if in case you're short on storage, you can always tweak this number. That way you'll be able to write limited amount of file. Whereas in a steady state case, if you're not interested in the development of your flow or something, and you just are basically your only last file is more important, your final file that is generated. So in that case, you can set the write interval to a very high number so that once your simulation is done, you'll only have your very first file and you'll have your very last file. So though in those cases, your write interval plays a big role. Hope that answers your doubt. Does anyone else have any doubts?
So, when I changed the time step, I'm getting a lot of files inside the pipe flow file. Name it. It has a lot of numbers.
Lot of numbers.
Like I'm getting a lot of files like 0.01, 0.1, 0.02, 0.2.
Correct. That only recently Ivan was explaining. Let me show you also. Currently, you have changed delta T to 0.0005, right?
Yes, sir.
So So this right interval is nothing. So based on that, you have to change this right interval also. So right interval currently it is 5. Okay. So after
Yes.
every 5 iteration, it will going to save one file.
Okay.
So now you have reduced your delta t to half. So instead of saving one file after every 5 iteration,
Okay.
so after reaching 0.001, it will save 2 files. So that's why the number of files are getting increased.
Oh, okay. Okay, sir.
Okay. So change it to 10 or 20 also.
That's fine. Fine, no, sir. If I change it, like,
Yes,
will
yes,
it
yes.
make
This
any
is fine.
difference?
No, it will not make
Oh,
any difference.
okay, sir. Thank you.
Okay.
So basically, if we are changing the right interval, it is going to save our disk space also, right?
Yes,
One way
yes,
or
correct.
another. Okay.
It will save your disk space.
Okay. And just one more query regarding this right interval on
Okay.
curiosity. So, what will be the? I mean, like, how far the interpolation will be affected based on this right interval? Say like, say in the previous candidates case, if we are saving uh, at 10 or 20 something, then
Okay.
uh, if we are solving a very little bit complex case than this pipe flow, then how about the solution interpolation? How it will get affected?
No, it will not get affected by saving at what time step you are saving the file.
But the visualization and rest of the things gets dependent
So
on this time
it will
steps.
depend on whether you are running the steady case or unsteady case. If you are interested in checking for each time step
Okay,
how the flow is varying or how the flow fluctuations are there, then you can save more files. If you are only interested in the final result, then you should
okay,
save less time, less file or the only final time step.
okay. Fine. So basically, what you are saying is, if our simulation is transient, then we can have more
Yes,
considering the disk space availability as well.
yes,
You are
yes.
saying, okay,
Okay, Mr. Malkeet, you were saying that instead of writing it after a few time steps, if we could write the time average data. So there are multiple ways to do that. So there are some functions also in which you can do that. So you can always explore that. As I said, that functions part in the control dict. So in that you can specify some particular functions that you have. Okay, so you can look into that as well. Yeah.
Okay, so now we are concluding the session for today. Thanks. Bye bye.